let's go to our next speaker then, Professor Peter Lodahl from Niels Bohr Institute. He's going to talk about single-photon quantum hardware for scalable photonic quantum technology with the quantum advantage. Professor Lodahl, the stage is yours.
Thank you very much. Katarina, can you hear me? Yes, very good. So you see my presentations as well? So thank you very much for putting this wonderful conference together, and thanks a lot for the invitation. I will speak about single-photon quantum hardware. And the platform I'm representing is a deterministic platform based on quantum dots embedded in photonic nanostructures. So a good old platform that we and many other groups have been working on for quite some time. They work very well nowadays in collecting photons. So the beta factor, the probability of coupling photons into a propagating mode, the waveguide can be really high. So this is a figure of merit for a deterministic single photon source. But it's also a more general figure of merit because the beta factor is linked to the quantum cooperativity by this simple formula. So if beta is close to 1, then this quantum cooperativity can be really high. And the quantum cooperativity is a figure of merit not just for single photon sources, but also for photonic quantum gauge, multi-photon entanglement sources, and so on. This simple relation only holds in the case where we have decoherence processes totally under control. So if we have a transform limited emitter lines inside the photonic nanostructure. And this is really the good news that the quantum dot platform has brought in recent years, is that you start to have these decoherence processes very well under control. So there are phonons, there are charge noise, and there are nuclear spin noise, and you all need to suppress this leakage significantly in order to make use of this quantum cooperativity. And I think that's a tool that we now have available in the quantum dot community, and we actually put on arXiv a perspective article trying to point to some of the opportunities that we believe that this new building blocks enables in photonics. So how to reduce these processes, these decoherence processes? Well, the name of the game is heterostructures that you, and it's a PIR, you can make PIN heterostructures very convenient in gallium arsenide, and in order to apply an electric field across the quantum dot. And this is what you're seeing here. We have these heterostructures, we have these membranes, and it has three salient features essentially. You're sweeping away carriers from the vicinity of the quantum dots to reduce charge noise. It also allows you to do electrical tuning of the quantum dot lines. And finally, you can deterministically prepare a single spin in the quantum dot and start to do spin physics on the platform as well. So a few highlights from the photon source part of our work. So these are the nice photonic waveguide, photonic crystal waveguide structures that we are implementing contacts on. We can optically excite a single quantum dot and emit the photons into a propagating mode. And you can also couple them out very well with specially designed waveguides to produce photons in an optical fiber, for instance. So this is a typical number of 10.4 million photons per second coupled into a fiber when we do strict pulsed pi pulse excitation of the quantum dots to drive that into saturation. We see the Hamburg-Brown twist measurements showing very good single photon purity. You have less than 1.5% of multi-photon contributions. And this can be even better. I mean, we can go to the 0.5% level and also beyond. And then I think a very important point is also to look at the correlations at longer time scales. So if you measure T2 also on longer time scales, you will, if you don't have the electrical charge noise very well under control, you will tend to see blinking processes going on these longer time scales. And here you see an absolutely nice and flat T2 over to hundreds of microseconds, really showing that you don't have blinking processes on longer time scales. The photon indistinguishability, of course, we measure in a Hong-Mantel setup. We have an asymmetric Mach-Center interferometer with a variable delay here, so we can measure the photon indistinguishability between subsequently emitted photons and also between photon 1 and photon, like out to photon 115 we had tested in the chain of photons emitted by this quantum dot source. And we see a very good indistinguishability, above 96%, reaching out to, well, 115 photons is the longest we go. We see the indistinguishability is really nice and flat all the way out to 115 photons, because the noise properties of these devices are very, very good. We also understand the fundamental decoherence processes, if we wanted to get closer to one, and that is phonon decoherence processes. And then we even also have ways of getting even better. We have 98 today, and we can go also beyond that by doing phonon engineering. So that was indistinguishability. How about the line width of these quantum dots? You can conveniently measure them in a transmission geometry, like what you're seeing here. We have quantum dot photonic crystal waveguide session here. We shine a laser through and scan it through the resonance of the quantum dot. It's a weak laser, so on average 1 photon interacts at a time with the quantum dot. And you scan the laser through resonance, you see these strong extinction dips when you hit a quantum dot, and you are measuring the line width in a very sensitive manner from measurements like that. And actually, these line width measurements are, in a sense, harder than the indistinguishability, because you're really probing noise processes also on much longer timescales than the nanosecond timescales that matters for the indistinguishability. Here, you really need to have charge noise processes also on millisecond timescales under control. And it's really exciting to see that you have, well, near transform limited emission lines in these photonic nanostructures here. We are comparing to, by doing time resolved measurements also, we are seeing how close are these lines to being transform limited, broadened by only spontaneous emission. And we can within 10% reach transform limited property in the nanostructures. And we have measured this on really many different quantum dots. And that's really about these heterostructures and low noise devices that can be fabricated today. So we also benchmarked what are the performance of such a source. We have benchmarked to what extent you could do a boson sampling experiment on that and take that into the regime of quantum advantage. So that requires about 50 photons to be in the quantum advantage regime. And here we have calculated the variational distance separation compared to an ideal boson sampler as a function of number of photons. So 1 would be the ideal boson sampling, but of course we have imperfect photons because of this finite indistinguishability. So when we add more and more photons to the boson sampler here, this variational distance goes down. And this is a blue curve that's from our source, and this is the current best experiment, boson sampling experiment with quantum dot sources. Brilliant experiment from the Chinese group, where they in a micropillar device did a 20 photon experiment, but in their case the indistinguishability actually decreased out in the chain, like I was talking about, unlike our source. And that actually means that you get a much faster decay of this variational distance separation while having higher indistinguishability. I mean, you can scale out to further photons. And then you can ask the question, so that's the indistinguishability, are the photons good enough? And the other important spec is, of course, the efficiency. How well can I couple photons? I can deliver photon into the boson sampling setup. And you can ask, so what efficiency do I need to reach in order to plug our source into the boson sampling setup they're running in China, in Jianwei Pan's group? And the answer is that at the quantum advantage threshold, you need to produce 78% photons coupled into an optical fiber, which is achievable with the performance. Again, for the 96% indistinguishable photons I was talking about here, this is achievable with the devices that we are developing. And you can say you're already generating that resource with higher than 80% efficiency on chip. Coupling it out to a fiber could be done as well. Question is, of course, if there are sufficiently good reasons to do that and really prove that explicitly, boson sampling quantum advantage with your source. But the bottom line here is that the technology allows it. The quantum performance is good enough to reach quantum advantage regime. And we have also commercialized this. So there's a startup company, Sparrow Quantum, that is commercializing these chips, chip technologies. So if any of you are interested, you know where to find it. So the second part of my talk, I will tell you a little bit about further opportunities. So this was about photons and scaling photons into quantum advantage regime. But of course, as I emphasized in the beginning, what we can deliver here is photon emitter interfaces with a high quantum compactivity. So you can do more advanced resources with these quantum dots. You can start to have tunneling a spin inside the quantum dot and do spin physics and have a level scheme like that. and I will show a little bit of the opportunities that this gives rise to. Of course, you need to be able to, or you can optically control this spin, and you need a long lifetime of the spin so that you can do your operations. You also need a sufficiently long coherence time, T2 and T2 star. And this is, you can say, the Achilles heel of the quantum dot platform that we're speaking about, nanosecond timescales, T2 star. But actually, there are workarounds that you could still produce some quite exciting states despite this short T2 star time, because we can do the operations in the photon emission so fast. 100 picoseconds timescale would be a typical recombination time of quantum dot in a nanostructure. So what can you do with such a source? Well, you can do multi-photon entangled state generation. There's a beautiful protocol of Lindner and Rudolph that if you do a pulse sequence like this, you have excite emit on a transition here. You can do spin rotations between two spin ground states. Then you can actually on demand produce a multi-photon entangled state where, like a GHZ state, like indicated here, spin is up. A photon was emitted in an early time state, and the second photon in an early time pin, a certain photon in an early time pin, and so on. If the photon was spinning down, it emitted in late time pin. So this time pin encoding of photons. And we really worked out how does that scale up in the presence of all the imperfections that we will have in these structures. And one particular imperfection that is important is what we call this B factor here, which is the branching ratio of the cycling transition, because you would like to have a cycling transition that you can emit and excite photons on. That's this channel here. At the same time, you would like to do spin rotation, so you would like to be able to drive Raman transitions to control the ground state spin here. So a figure of merit is really the branching ratio between emitting on this transition and emitting on a different transition here, on the diagonal transition. And you want this B to be as large as possible. And actually, the photonic crystal nanostructures have this inherent asymmetry, so you almost get it for free, a large branching ratio like that. And if you're analyzing the entanglement infidelity for an n-photon state, you can write up an expression like this, and you will see that this branching ratio enters, and you need that to be large. There are other mechanisms, error mechanisms as well. There's a detuning of a fourth level here that you want to be detuned far away. There's an indistinguishability of the photons. And if you put that all together, you will see that you will get estimated 1.6% error per photon, which interestingly really is starting to approach the threshold for fault-tolerant measurement-based quantum computing. So there's really a way forward with high rate producing these multi-photon entangled states deterministically with these quantum dot sources. And T2 star was not in the game here, and this is interesting. I can comment more on that maybe in question session. I mean, there's actually a spin echo implemented directly into the protocol here. So what could you do with such a resource? Well, that is, I think you heard a lot about this already at the conference here, these exciting measurement-based quantum computing architectures. You produce an entangled state up front and do single qubit measurements. Only on that's your algorithm. And I think you can think of the quantum dots as producing in a very flexible manner on demand these small cluster states. And then you could use fusion, linear optics fusion, probabilistic fusion, to start to fuse together such small cluster states into a large universal cluster state for your quantum computing. I think that starts to become a viable approach towards quantum computing as an alternative to the spontaneous periodic down conversion methods, where of course you had to use a lot of photons already to generate the clusters, and they're due to the probabilistic nature, you generate them on demand. So of course, the engineering challenges ahead, and I've listed a few of them here. Well, one is that these use high quality quantum dots devices. Quantum dots are randomly spread across a wafer, but nowadays you can optically address these quantum dots with very high precision and then fabricate your nanostructure around it as indicated here. There's also how to excite these quantum dots very efficiently. I mean, typically you come from the top and address these quantum dots with precise optical pulses, but it's really nice if you could have a plug and play device where you're sending in an excitation pulse with one grading, resonant excitation pulse and one grading, and then out comes indistinguishable photons on a second grading. And there's actually a method for that, and we even have a patent on this, which also is a way of scaling up to exciting more quantum dots, because you could then divide the excitation laser up to many different ports. And multiple emitters, okay, addressing more and more quantum dots and start to couple them to each other, requiring these kind of technologies of positioning and also local tuning with electrical field and strain. That is clearly required as we are moving, scaling up. But remembering that, you know, one quantum dot can emit really many photonic qubits. So I mean, it's not that one qubit is one matter qubit is one qubit to do experiments on. One matter qubit, one quantum qubit will produce really thousands potentially of indistinguishable photons. That would be the resource that you're generating, and then scaling up by adding more photons, more quantum dots, sorry. So I'm almost at the end of my talk. This is a scaling up approach we're foreseeing, and again, have a look in this manuscript on arXiv. The idea is to have source chip with the quantum dots here and various functionalities, maybe of filtering and switches, and then couple that, of course, to advanced photonic integrated technology in other platforms like silicon nitride, lithium niobate, or silicon eventually, and move the wavelengths to longer wavelengths, and really exploit all this advanced PIC technology that is available, and having a heterogeneous combination of the active excellent sources, quantum sources, and the passive circuits. So this is my summary slide. So it's essentially just a one-liner here that I think it's time to scale up these deterministic single-photon sources, single-photon hardware, and towards some applications. And I would like to thank my collaborators on this project. Thank you.
Thank you very much, Professor Lodahl. I cannot see any questions right now, but I have a couple of questions. I was very interested in seeing your investigations about measurement-based quantum computing and the creation of graph states. I was just wondering, do you have any plans of using this framework for quantum networks, for example?
Yes, absolutely. So that's an interesting approach to quantum repeaters, actually. So that is also it's called one-way quantum repeater architecture, where, as opposed to the traditional repeater protocols requiring a quantum memory, then the idea here is that you encode in these cluster states. You encode the information in these cluster states. That makes them very fault tolerant, and you can send information encoded non-locally in a photonic cluster state and construct a quantum repeater based on that. And actually, we have also recently worked out a blueprint for exactly such a quantum repeater architecture, really breaking down in the hardware and say how good photons do you need, how good gates do you need, how long T2 star, and really starting to say how would you build that based on quantum dot hardware. This is challenging, but it's doable. It's not science fiction, and I think with quantum dot hardware, and I think that's a good starting point.
Absolutely. Great, thank you very much. I don't see any more questions appearing in the Q&A chat on the right. Maybe we're just too weak. I just wanted to remind the audience that they can vote up for questions. So in case we have more questions appearing right now, you can just like vote them up and they can go up the list and they can be asked first. Yeah, so I think that's all for now. Thank you very much, Professor Lodahl.